Welcome to Magic of Electrons Activity 2.2, Switches, Diodes, and Light Emitting Diodes. This is an assignment from PLTW. Introduction. You have probably noticed that taillights on cars and some traffic lights look like a collection of tiny light bulbs. Actually, those small lights are light-emitting diodes, which we also know as LEDs. In this activity, you're going to explore the use of LEDs. So for our snap circuit, we're going to need our board, voltage source and power supply. We are going to need a motor, okay, a fan blade, various sizes of snap wires. Got all sorts up here. Okay. A slide switch. A push button switch. A diode. An LED. I chose red. You can also choose green. And a 6-volt, 1/2 amp light, which we have right there. Okay. All right, and we will again be using our schematic symbols chart, and we have a PowerPoint that goes with this lesson. So in teams, we are going to create circuits and using switches and diodes and LEDs. We are going to do this doing engineering using the presentation that is up here. So I'm also going to have my engineering notebook. As I've said before, it can be on any type of paper you would like. Okay, so right now, let's go to our PowerPoint. All right. So in this PowerPoint, we are going to talk about switches, diodes, and light emitting diodes. Okay, so this is intended to use with the PLTW Activity 2.2 for Magic of Electrons. So we have 4 types of mechanical switches. Okay, so a switch is just a mechanical device used to connect or disconnect a component or a circuit. So some of our common switches are a push button switch, okay, the slide switch. I usually see those on the bottoms of children's toys on the battery pack. A rocker switch makes me think of a power strip, and a toggle switch is similar to a light switch. Okay, so there's all sorts of varieties of these, but these are our 4 main mechanical ones. Okay. So in our circuit engineering notebook, draw a circuit diagram that will power a lamp using a slide switch and a 3-volt DC power source. Okay, so right now we're just doing diagrams. So I am going to switch back so that you can see my notebook. All right, so I want a slide switch, a lamp, and a DC power source. So from our previous lesson, we know that a DC power source symbol looks like this. Okay. Next, we want a switch. Now, if you noticed on that slide, a slide switch has this symbol. Okay. And we want a lamp. Okay. So that's our schematic for that one. Okay. And if you want to make a notation on your diagram about this 3 volts, because it will make a difference as to where we connect it to our power source. Okay. The next one we want to do is a circuit diagram that will power a motor using a push button switch and a 3 volt DC source. So our symbol for a motor is M. Okay. So let's go back to our notebook. Okay. So again, let me zoom this in just a little bit. We're going to use that DC power source. I'm going to mark over here that it's 3 volt. Okay. And we want a push button switch. And a motor. And a push button switch looks like that. Okay. So let's go back to our diagram. So now let's talk about diodes. A diode is a device that permits current to flow through it in only one direction. Okay. The symbol for a circuit diagram is this right here. Okay. Now, diodes work with a procedure called doping, and it has to do with where charges are located. The other place that you can get more information on that is back here, okay, the purpose of the diode. As we learned previously, there's a p-type and an n-type of doping of silicon conduct electricity. They just differ in how they conduct. However, when the p-type silicon is formed in a chip with an n-type silicon, the electrons flow through the silicon in only one direction. This is called the principle of the diode. Where these two types of silicon intersect is the p-n junction. Here's how the diode works. A diode is like a one-way valve for electricity. Current can only flow through it in one direction. Here's a simplified explanation for how a diode conducts electricity in one direction, forward, while blocking the flow of the current in the opposite direction, or reverse. Okay, so as we talked about before, our electrical charges, when it comes to a DC power source, flow from positive to negative. Okay. Here, the charge from the batteries repels the electrons and holes towards the p-n junction. So we have our negative electrons coming over here. We're getting push. Okay. If there's enough voltage, the electrons will cross the junction and current will flow. Okay. So we've got our electrons coming from here, jumping this junction, okay, and going this way. Okay, because the goal of these little negatives over here is they want to fill these positive proton holes over here. Okay. So if you look at this symbol like it's a funnel, all of this charge is coming from this direction and going that direction. Okay. But in this image, there's no current flow. Here, the charge from the battery attracts the holes, Okay. So we have these negatives and these positives, opposites attract. Okay, and same thing on this side. So since the battery attracts the holes towards the negative and the electrons towards the positive, both are moving away from this middle part. So no flow can go. Okay, a lot of teachers that I've seen online have referred to this little line as the can't line. It cannot flow from the line back into the funnel. It can only flow from the funnel across the line. Okay? Diodes are commonly enclosed in a small glass cylinder. A dark band marks the negative terminal. The opposite terminal is the positive. There are many different types of diodes which are used in many different applications. One type, the rectifier, is used to convert AC power to DC power. So let's draw a schematic for a circuit that uses a DC source to power a lamp and includes a diode. Okay. So we have our same 3-volt DC power source. Okay. And the trick would be that your diode wants to point towards the negative end. Okay. So if I put my diode here, I'm now pointing to the negative side of my circuit. And here is my lamp. And there you go. That's with the diode. Okay. Now, an LED is a special kind of diode that lights and is used in a circuit to show that a circuit is flowing. LED stands for light emitting diode. An LED sometimes has one leg shorter than the other, such as this. Okay, you can see that even though they're a little bent, this leg is longer than the other. Okay, the shorter leg is the negative leg, and the longer one is positive. The negative leg might also have a flat side on the plastic cap, so it's kind of hard to see. I don't even know if I can get it in the right position, where you can see that this side, like right here, is flat, where over here it's rounded. Okay. It is also important to connect the LED's legs in the right way in a circuit, negative to negative and positive to positive. Okay, so let's draw a schematic for a circuit that uses a DC power source and includes a diode. Okay, so let's take a look at this. So we've got a DC, we've got our plus and our minus. Okay, it wants a diode, so we want to go this way. But then it also wants an LED, which means our symbol changes up a little bit to have arrows pointing out. Okay. Now, we can draw or describe a diagram that shows the conventional flow theory. Now, to get to that, we have to go back to our diodes here. Okay. And this is similar. This is the diode with a lamp. Okay, and we've already talked about this, about making sure it goes the right direction. Okay. These are all examples of LEDs. And this is similar to what our diagram should look like. If you notice, the symbols for your circuit diagram are right on the snap components. Okay, so conventional flow theory is the idea that we've already talked about. Okay, about 200 years ago, scientists theorized that electricity had both positive and negative polarities. Okay, at that time, they just arbitrarily decided that electric current flowed from positive around to negative. Okay, while it was never actually proven as a fact, the theory was accepted for quite some time. Okay, so this is the conventional current flow theory. And this kind of makes sense. Okay, as our positives push out and around, or excuse me, as the negatives are getting pushed from this side by the negatives, I'm going to come out this way and go back around. Okay, which makes sense because we know electricity comes from electrons, and electrons are negative. Okay, okay, but now we have the electron flow theory. Okay. As our knowledge of science progressed, and with the discovery of the atom and semiconductor electronics, it became apparent that the conventional current flow theory was incorrect. It is widely accepted that it is the electrons that actually moved, flowing from negative to positive, not from positive to negative. Okay, this newer theory is known as electron flow theory. The emergence of this new theory caused a controversy that is still in existence today. For over 150 years, all circuit designs have been based upon the old conventional current flow theory. Okay, and if you look at the descriptions from how the doping works, it's very similar to a battery. So it would make sense that those negatives are going to push out from the negative side, and as they move out, they become attracted to the positive side. Okay? And seeing how protons don't move, this would make more sense. Okay? So regardless of which theory is used to explain the phenomena of electronics, the most important point is the correct polarity must be maintained when building circuits with devices that require a definite polarity. Okay? In the case of the schematic for the diode, the arrowhead is actually pointing against the current towards negative. The line that crosses 90 degrees in front of the arrow can be interpreted as can't, meaning the current can't flow in that direction. Okay? So let's go back to our lesson. Describe or draw. You can actually use the diagram straight from the PowerPoint. Using the schematics you drew, you are going to build the following circuits. So let's raise this up a little bit so we have some more space. Okay, this was our first circuit, second, third, fourth. All right. So let's start with this first circuit. Here's our breadboard from the last lesson. But if you notice, our 6 volt is facing this way. Our diagrams, however, all show 3 volt, which is over here, hard to see behind the plug. So I'm just going to turn that around. Okay. So our first diagram was this one. DC power source with a slide switch and a lamp. Okay. So we are going to connect here, here, and here. Okay, so now I can turn my light on and off. Okay. Make sure you take a picture of this for your assignment. Okay. The next one is the motor with a push button switch. So take these both out. Okay. Here's our push button. Here is our motor. Let's connect these in. All right, and then we've got some observations. Okay, so let's push our button. There we go. Okay. Now it's saying turn the motor around in the circuit. What happens? So it turns this direction in the way that I have it set now, right? Turns clockwise. So let's turn it around. Okay, now it's turning counterclockwise. Okay. Okay, so the first question, turn the motor around in the circuit. What happens? Does the motor still work? Okay. Does the motor have polarity? Meaning it has to be hooked in a specific way in order for it to work. Okay. Tell me what you think. The next one is the diode with the lamp circuit. Again, make sure you take a picture of this before you disconnect it. You'll need it for your assignment. Okay. So now we want a diode with a lamp. Okay. So let's snap this in here. So here's our little glass tube. Okay. Let's connect this in. All right, I'm all connected. It's not lighting up. So, did it turn on the first try? No. So let's turn this diode around. Okay. And now it works. It's also not as bright as before. Okay. So, did it light on the first try? Turn it around. What happened? Why? Think about what we explained about the diodes. Okay. And now they want a diode with an LED circuit. Okay. So let's take out this and put in this. Okay. Just pop it on there. Okay. Did not light up. So turn this around. Okay. Now I've turned it around. What happens? Okay. Explain what is happening in 2 and 3 when I turn them around. Okay, so I've turned the LED around. Now, when I turned it on, Then I turned the diode around and it went back off. Okay. Why? What is happening? Think about what we're talking about here. Okay. In math, multiplying two negatives makes a positive. Explain what happens if you turn both the LED and the diode around in the circuit. Okay. Okay. So the question is, if I've turned both of these facing this way, what's going to happen? Now, if it is set up correctly, these should flow from positive, 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 around to negative. Okay. And in this case, they light up. Okay. But then they ask, what happens if you turn them both around? So this is facing away from negative. This is facing away from negative. Let's see what happens. And that's the nice thing about these snap circuits. You can always see what happens. All right. Still does not turn on. Okay. Think about it. Why does that happen? And now we are to our conclusion. So number one, diodes can be used to protect electronic components from current flowing in another direction. Describe another application outside of electronics where it would be important for something to flow in only one direction. Okay. Describe three objects in your house that utilize LEDs. Use the internet to research the use of LED systems to replace general household lighting. Describe one advantage and one disadvantage of replacing standard light bulbs with LED lighting. And what are the two ways to determine the negative leg of an LED? Thanks for following along with me. Ask your teacher if you have any questions.